So welcome to this lecture video on model-based reinforcement learning. And here we talk about the real-world application of model-based RL, and in particular with dealing with uncertainty in model-based reinforcement learning. So this is our outline. We're almost at the end, and here we talk about the real-world application. So the general problem we still didn't yet not focus so much is that our models that we actually learn, that they are never really perfect. And I mean, there is like uncertainty in our models. And if we talk about uncertainty in our models, we actually have to differentiate between two different kinds of uncertainty. The first one is the aleatory or the process uncertainty, some kind of risk, as the process that we're looking at itself has noise. So we have stochasticity in our environment, and this stochasticity also leads to the problem that we might end up with uncertain models. So in other words, or maybe to make an example out of it, just imagine that you shoot 2 times with a cannon. And however, if you do this, and for sure you will not really consider all the parameters such as the wind and the pressure and things like this, you would not really consider all of them to be really the same. So you will also not expect that the two balls actually will stick to the same exact trajectory. So in other words, we have an inherent stochasticity in our world, and what we actually have is we are really actually ending up with a distribution of our outcomes. This is a irreducible kind of uncertainty because the uncertainty is just there, and it's usually a static uncertainty. So on the other side, there is the epistemic or the model uncertainty, and this is the thing that our model is just not perfect, or it's just not really accurate. And this usually results from a lack of training data in certain, or a lack of training data, especially in certain areas of the training domain or the input domain. And this is really critical in areas outside the input domain where we have, and if we run something like neural networks, where we really get an extrapolation error in our predictions, and this really has a lot of influence on our models and hence on our model-based agents. So in other words, we can describe it a little bit as the model's lack of knowledge about the world. We can maintain a distribution over beliefs, and in principle this error is a reducible error. So we can actually reduce this error if we gather more data. And it might also change with learning, so it's not a static uncertainty in contrast to the aleatoric uncertainty. So the aim to understand this point is, where does the data to train the models actually come from? Can we also act with imperfect models? Do we need to model uncertainty? And if we need to model uncertainty, how can we estimate it? And can we actually combine background and decision time planning and use model uncertainty as a measure to actually do better model-based RL? So to actually do this, we have different things which we can actually do. So first, we can act under imperfect models. So something like online replanning, which is something that we will introduce shortly in these slides. So a very popular algorithm to actually do this is model predictive control. Model predictive control explicitly assumes that our model is imperfect and we continuously replan during deployment. The second idea is actually to estimate the model uncertainty and to use it for safe and efficient planning. So while model predictive control doesn't really exploit the fact that you could estimate and propagate uncertainty in the network, we could actually come up with network or methods to estimate uncertainty. And if we can actually estimate this uncertainty well enough, we can also use it for safe and efficient planning. And of course, we can combine A and B. So to actually understand aleatoric uncertainty and epistemic uncertainty a bit better, there's a nice slide that actually just visualizes this. So if you actually sample data points in here from an environment and you fit a model to it, and the model should or could look something like this, There is a process uncertainty and aleatoric uncertainty, because actually if you sample from a certain point, you get different values actually for this point. And this kind of distribution is actually describing the aleatoric uncertainty. And the question is, can you actually model this one? And the epistemic uncertainty is actually the thing, especially it's around the borders, or when it's out of distribution of your model. It's actually what your model is actually predicting outside the area where you actually have seen data during training. And if we're talking about model-based RL, uncertainty in our model is something really crucial, because we're actually, as we have seen in the previous lectures, in the previous lecture videos, we do several steps of prediction with our model into the future. And the problem is that if we have small errors in the beginning, or always small errors during certain one-step predictions, these small errors actually propagate through the trajectory sequence, and they actually compound. So they actually become even larger. So there's a nice this is the so-called Muchoku hopper example, where you have a single leg that's actually trained to hop through the environment. And what you see here is actually the uncertainty, or the difference of your model towards the real environment as the prediction steps towards into the future. And you see that with longer time steps into the future, the errors are getting larger and larger, as visualized as the colored bars getting bigger and bigger. And there's actually two problems out of it. The first problem is, I should have switched this around. The first problem is that the longer your rollouts are actually, the less reliable they become. Because as the model predicts more into the future, the error also becomes larger. But there's another issue actually, because actually you have a planner that is used to actually select an action sequence. And what you see a lot in reinforcement learning is that if you have errors in your model, that your policy, when you search for the policy, usually exploits the errors in your model. And if you have a model that's correct, or if your model has slight deviations at certain points, it turns out that the policy search algorithm actually exploits such errors in the model, and you will come up with an action sequence that's completely useless in the real world. There is another nice way of visualizing the thing with uncertainty. This is a nice example known from supervised learning, which gives you a little bit of intuition why. Or put it differently, the basic idea could be, why couldn't you just use the entropy or the energies of your neural network as an indicator of how certain actually your model is with a certain prediction? And it turns out that these energies at certain layers in the network are not that well calibrated. So actually, meaning that so there is actually work from supervised learning that presents you data from images such as dogs and cats and things like this. And the thing is, what we have seen is that with networks getting bigger and bigger, so you see a LearNet on the left side, and you see a ResNet on the right side on CIFAR 100. And what you see is actually that the average confidence and also the accuracy of your classification tasks, they increased a lot over the last decade. But what you also see is that while models were very well calibrated back in the days, they are not so well calibrated now. So this means actually that this plot actually says that if my probability of detecting a cat or a bucket of cats is around 60%, I assume that in this bucket around 60% of all the classes are detected correctly and 40% are not detected correctly. If you have such a thing for all of your certain buckets, you can say your model is well calibrated. And this is not the case in modern architectures, and it's also not the case in the architectures we usually use for reinforcement learning. So with larger networks, the calibration of such networks, which actually indicate the uncertainty of the model, they become actually useless. And in reinforcement learning, we actually want to usually overfit our models to the environment, and this requires large network capacity to actually do this, and this also means that they are not really very well calibrated in practice. Moreover, many methods that we use in supervised learning to actually guarantee calibrated models are actually post hoc methods that are not that very well applicable to the RL setting. So the question is, if we have now the problem that we have models that are not very well calibrated and maybe they are not that well formulated, can we use such models even if they are bad? And the question, and the answer is of course we can. So maybe just recap our initial idea of doing background planning with policy backpropagation. So this was the idea to assist an agent so we have a differentiable model of the environment, and we can use a policy gradient-based method to actually use smooth derivatives of our forward models of the environment of the forward model of the environment and the reward function in order to do the smooth updates with respect to our policy. So the algorithm actually looked like this. So we run a base policy, which was in the beginning a random policy, and we collected data samples D. From this data samples, actually, we learned a dynamics model, which was F parameterized by parameters theta, and our optimization goal was just to minimize the mean squared error. So we wanted to just to predict one step forward dynamics. What we then did is during policy optimization, in order to optimize pi theta, we actually backpropagated through our forward model into the policy. So we have the our optimization objective in here, and we backpropagated all the way through our model into the policy. Then we run our updated policy in the real world, which gives us actually new visited tuples that we can actually use to learn and retrain our dynamics model. And we keep on doing this. And the thing was, or the problematic was, in this case is, the problem is, remember that we actually make mistakes. So our model is actually not providing very well calibrated or very good gradients at certain points of the area, which actually leads to the problem that these gradient updates might simply be wrong. One way to actually go around this is not to do really background planning, but to do policy backpropagation and maybe run a better algorithm for online planning. And this algorithm is actually called model predictive control. And the idea of model predictive control is not to just bullheadedly rely to a committed plan, but always to replan online. So in fact, model predictive control really looks very similar to what we did in the beginning. So we just run a baseline policy, which is a random policy, and we collect our data. Based on this data, we learn a dynamics model, just as in the previous one too. So the first two lines do not really change. And instead of planning through our forward model to choose all the actions, we just plan until some time horizon h, which is usually much smaller than the sequence length, using our model. Then instead of executing all those actions, we just apply the first action of our plan. So we just do the first thing that we can actually do, because for this action, we actually are very sure we do not have so much compounded errors that are actually part of our actions. So actually, our model did not really have so much compounded errors that have an influence on the action that we actually computed, and we just do the first one, they apply the first action, and come up with a new plan with a new time horizon again. And we do this in an inner loop, and if we are done at some point, every n episodes or something like this, we take all the new visited tuples that we get from the environment and learn a new dynamics model from this. And it turns out that depending on the accuracy of your model, you can really like deviate a little bit, and like you can actually choose a larger time horizon for planning, depending on how good actually your or how well calibrated or how low your uncertainty of your network is, or you can apply more than one action to the plan immediately in order to improve computation time. Okay, so MPC as a little as an example in model-based RL. So just as in the beginning, we have some state we are currently in at this point, and we have some goal state. And what we usually do is, in the beginning, we optimize the trajectory. So in this case, actually, I need to see. So we have some time horizon h, and we just compute the actions that we think leads us best to our goal state in here. So we optimize the trajectory. Depending on the computation time, we will come up with a very decent, we think with a very decent version of our plan. And what we then is, we send the first optimal action of our plan to our actuators. And what we see here is that already the first action does not really take us to the point where we actually thought we might end up in. And we could actually go on with our actions, but this would really take us to a very different situation. And instead, what we will be doing in here is we will just use the new state and actually come up with a new plan. And this new kind of or new sequence of actions is now computed over our time horizon, and we simply apply the first optimal action of our plan, which completely lets us again end up in a new situation. And we can do this all over again until we actually reach our target. So in the end, the chances are very high to really end up where we want to end up in. And in retrospect, also being said, if you now look at the trajectory that you actually went, you did actually do the things really completely different as we would have done them in the original plan. So this was the original plan. And the question is, if so the thing is, in MPC, errors do not really accumulate because you actually use a large time horizon with a model that is uncertain, but you use it just for planning, and you only take the first immediate step to your action, and then you replan again, and this actually lets you actually reduce the model error, and errors do not really accumulate over the time horizon. And it also turns out that in reality, you do not really need a perfect model in this sense, because actually you replan all the time. And actually what you need is, you only need a model that's somehow pointing in the right direction, because actually, as you always only take the first action out of your plan, it really turns out that you can also go with a model that's highly uncertain in certain areas, because you always keep on replanning. This sounds expensive. Yes, it is. It is expensive, of course, but it is not that expensive as you might think first, because there is actually ways to reuse solutions from the previous step as something like an initial guess to come up with solutions. So this is somehow encapsulated in here. However, to make it more visualizable, so if you have a current guess of how actions to take, you can use these actions to take from this position as an initial guess starting from here, and then you can come up with an updated plan that actually and you can just optimize from there. So exactly, so actually this you can do in here, and there's also like pretty decent applications on this. Usually you see such MPC applications in robotics or in hand manipulation tasks. Or what you actually see here is a very nice example. You see it on a racetrack. And what you see here is you see a neural network, a rather small neural network, and you see, in fact, a planner that, in this case, I think they tried really to go around the track as fast as they can. And you see the model, you see actually the trajectory rollouts for the MPC algorithm in this window. And what you do is you do a continuous replanning, so you actually always only take the first action, and then you do a continuous replanning of your trajectory. And you see that there is a slight deviation in there, but also, I mean, the final result looks pretty amazing. You have a car that's like really decently going around this track, always drifting a little bit, and I think it's really hard to go around this track any faster than they did it in this paper. Okay. So another thing is, so what we now did is we actually assumed that our models are uncertain, but we didn't really and how we actually went through it. We just did the horizon planning, and we just did the first action, and then we planned again. So in a sense, we tried to bound the uncertainty through a more often replanning of our through our model. Another option that we actually have is that we can actually estimate a plan that are a little bit more conservative. The first idea is actually to keep rollouts short, so that they actually don't deviate too far from where we actually have real data. This is actually, we can also do something like this. So we can actually, through planning, we can actually say, okay, so if our model now predicts in areas that are too far away from where we think we are certain, we don't want that, and we stop the rollouts. In this case, even a single step rollout can help actually to improve. This is what we did in Dyna. So in Dyna, we only had one step rollouts that we actually that we actually took into account. Another easy idea, what we could do is we could maybe also keep a distribution of models and plan. So we actually have a distribution of models, and we plan with the average or the worst case over the model uncertainty. So we could, maybe what we could do is like we could take ensembles, and we take more models to actually make smaller multiple steps through the environment. And we take the model as some kind of uncertainty measure. Or actually, we can also force our agent to act in order to stay close to the state where we think actually that our model is certain. This is something that we do not really cover in the lecture here. We can do this implicitly, so we can stay close to the past policy, which is something that you also know that we do not want to go too far away from our current policy, because then we also need to take into account that the data that we see is out of distribution. There's a nice work on this called relative entropy policy search or guided policy search. So if you're interested, just Google this one. And you can also do it explicitly. So you could also add a penalty of going into regions that you know that are unknown. There is an idea of model-based offline reinforcement learning, MORAL, I think, and this is also part of our lecture on offline reinforcement learning. However, the second and the third idea, so keeping a distribution of models or acting to stay close to the states, they actually both require an estimate of a model uncertainty. And the question is, how can we actually estimate the uncertainty of our model? And it turns out that there's actually more than one way of actually doing this, and we will cover a little bit of it in the rest of this video. So the general idea is actually to say that we have a model that's actually capable of estimating its uncertainty, which could be Gaussian processes. We can do it with Monte Carlo dropout, with probabilistic neural networks, or with ensembles. And if we have an estimate of the model uncertainty, we can propagate this uncertainty through multiple steps throughout our prediction horizon. So this is the general idea, and if we have an estimate of our model uncertainty and of our prediction horizon, we also can take this into account for our planning algorithm. So these are like representative methods or models that actually allow for a measure of uncertainty by design. I must say that at this point, I would say ensembles is a very popular thing to do. So actually train different combination of models with different training data and taking their disagreement as a measure of uncertainty. this is actually a very nice thing to do, which you see a lot of in practice as an easy way of actually doing this. Of course, Monte Carlo dropper is also a very nice idea, although this is a little bit, in my opinion, a little bit harder to be tuned correctly. Okay, maybe let's talk about probabilistic neural networks as one idea of capturing aleatoric or process uncertainty. Usually what you would do in practice, so actually this is the question is, how can we actually capture the stochasticity in the environment? So this is the general idea, and the idea is also simple. I will not go into the real details about how to optimizing such networks or how to dealing with the optimization of such networks, but the general idea is the following. So we have a neural network, and instead of just predicting the next state or an update to the next state, what we actually want to do is our state and action input should define a distribution over the state that we might actually end up in. And what we usually do is that we output a mean and a variance from which we can actually sample the successor state. So the loss function for training is something like the negative log prediction probability. And if you assume a data set D with pairs of such example data, what you usually would have for such a loss function, so if you actually assume a Gaussian, you can come up with such a loss function. And in the end, what you actually do is that you fit actually parameters of a Gaussian distribution around the training data, from which you then can sample, from which then if you apply it and you actually have a state and an action, you can put it in, you get a mean and a variance, and you can use this as parameters for a Gaussian distribution, for which you then can draw a sample to actually estimate the successor state. So in other words, you actually model the distributions over the outputs of the model. So this is what you do in here. And if you want to capture epistemic or model uncertainty, what you can actually do is you have your data set. You can actually use probabilistic neural networks for this too. This is also what I did a little bit in the beginning, what I said in the previous slides. So you can come up with an ensemble of probabilistic neural networks, and this also allows you to capture the epistemic uncertainty, so the uncertainty of your models depending on the data that you have seen. And what you usually do in here is that you have a data set of samples from real-world experiences, and you come up with random samples or random sample data sets from this whole data set. So then you have a number of M data sets, and on each of these data sets, you just train a probabilistic neural network. And then actually what you can do is all of them will actually output mean and variance of a Gaussian distribution that defines your output probabilities over the states. And you can actually see, depending on the outcomes, if you then put a state and action in there and you actually evaluate all of these networks, depending on if these networks agree on the results or not, you can somehow use this as a measure of uncertainty for your epistemic uncertainty. One thing to mention, so if neural networks actually predict Gaussians, in this case, you can get a multi-model Gaussian distribution out of it if you want to do that. So the question is now if you use such ensembles of probabilistic neural network models to actually capture or actually as a model of your dynamics, how can you actually propagate the uncertainty of your model across future time steps if you predict into the future? So what you usually see is, like starting from some initial state S0 and taking an action A, you want to evaluate your function, and your function will output a new state S1, and given a new state A1, it will output S2. Given a new action A2, and your model will actually output some state S3. And actually what you want to have is, you want to somehow propagate the uncertainty across this trajectory and draw. And what you actually want to do is, depending on your uncertainty in your network, you want to draw different trajectories. For the same action, you want to draw different trajectories that actually might end up that actually are a representative for where you might end up in reality. And there's actually two ways of doing this. So the one thing is moment matching, the second one is trajectory matching. So in the first one, what you actually want to do is, so you take your ensembles, and what you actually do is you sample a Gaussian from the first network, and what this actually allows you to do is, so there's a couple of means and variances coming out of it, and this actually lets you define a multimodal Gaussian distribution. And from this multimodal Gaussian distribution of these network ensembles, you can actually draw samples that you can put in again in your networks, which lets you come up with a new multimodal Gaussian distribution in the second time step. Note that actually this distribution tends to be much wider and having smaller probabilities overall through the prediction. And this is also a measure of how uncertain then your prediction is actually be. Another idea is to do trajectory sampling, which actually means that you just get a mean and a variance if you apply the first step. Then you sample from this distribution, put this in the second step, and you just go on along the trajectory to just come up with certain trajectories, samples of trajectories through your model, and this you can do for m times in this case. Okay, so this would be trajectory sample in order to propagate uncertainty through a learned through an ensemble of learned probabilistic neural networks. Okay, so how would you actually do this in practice? This is actually being done a lot, and this is a nice paper that also reads very well. So if you're really curious about it, just look into this one. So in principle, as a summary, what I just told you, it basically works. However, I must also say that it's really often only a crude approximation because the number of models is usually small, so lower than 10. But what you usually do is you have a dynamics model in here, and you sample from that model, and in this case you propagate trajectories. So you sample for the first step on this ensemble, and you keep on sampling from the distributions, and what you see is that the variance always increases, and then you can use this propagate sampled and propagated trajectories as an input for a planning algorithm for model predictive control. And what you see here is you can see how the deviation of your models actually tell you how uncertain actually your prediction of your trajectories is, because actually until this point in time, so they all start in here, so until this point mostly all the trajectory predictions until this point mostly agree in where the agent actually lands in. Okay. So another idea actually to use uncertainty information is actually to do a closed loop control with the propagation of model uncertainty. And there is a nice paper called PILCO, Probabilistic Inference for Learning Control, that exactly does this kind of things. So PILCO is a background planning algorithm that uses a Gaussian process as a state space model. Gaussian processes are really nice because they can actually come up with decent estimations of mean and variances with only little input data. So what they do is they do moment matching with the posterior. So actually, if you do the next state prediction and you will go on with this one, so the uncertainty is propagated using the moment matching idea that I just told you 2 slides before. Why do they actually use Gaussian processes? Because actually Gaussian processes have a very low extrapolation error by design. So actually what this means is if you get to data that is out of distribution, you actually fall back to the prior distribution where you are somehow in a safe area of acting. And the second thing is that the moment matching for RBF kernels that are used in the paper is actually calculated analytically, which makes it much more convenient to be used in practice. So here you see actually the moment matching idea and how you actually come up with the posterior to actually compute the prediction steps through several time steps in the future. So this is the pseudocode. It's not that much code in this case. I also recommend reading the paper. It's a very mathematical paper, so I think you need to read it more than once in order to understand it. But what you see very nicely, in the beginning you do some exploration, and what the exploration is good for, you just create data points, and you use these data points to actually create a Gaussian process-based dynamics model using all the data you have seen so far. On this you do the model-based policy search, and this is actually being always done. So you actually do the policy search, you gather new data, you fit a Gaussian process model, and you do this over and over again. And this actually helps you with only very little experience. I think they already have it in here. Maybe let's put it a little bit in the further into the future. This is really amazing results, because with only little total experience, in this case 17 seconds, you are really able to do the swing up of the pole and really balance the pole even with slight deviations in the dynamics. And just remember that this is not a simulation, it's a real pole, and it's a real system, and you're able to actually use the Gaussian process model and to propagate the uncertainty through several time steps into the future, and then you can actually come up with a planning algorithm that really outperforms anything that has been there before. Okay, so Pilko is a really nice example that really shows the advantages of model-based RL. Using uncertainty propagation. Its advantages are it has an unprecedented sample efficiency, so it's very hard or very difficult to actually come up with something that is really better than this one. And it is also robust to small model errors, because you have a Gaussian processes and you can actually propagate the uncertainty of your model, and this really helps in planning. However, there's also some shortcomings. Because you're using Gaussian processes and the training actually scales cubically with the number of training data samples. So with many training data, actually Gaussian processes are not efficiently trainable anymore. So however, in the low data regime, actually you get an unprecedented performance with Gaussian processes. There's only specific classes and policies and rewards functions supported, and it requires problems with very smooth dynamics, which is, however, something that you will find a lot in control tasks or reinforcement learning problems. I'd like also to mention that there is there's a work building on top of it, which is basically called Deep Pilko, and Deep Pilko is basically uses the same idea of Pilko, but it addresses the shortcomings of Pilko. The advantages here is actually that they actually scale to large data sets. They leverage GPU processing, and they allow for very flexible policies, and they are also still robust to small model errors. However, they also have some shortcomings. They have still high execution times. For instance, for learning 40 iterations in CardPole, Pilko needed almost 20 hours, in fact, while Deep Pilko needed still 4.8 hours using the GPUs, which is something that, of course, is much higher than what you can expect if you use some model-free algorithms. However, this is like GPU and CPU time and not sample complexity. And as you always do, as we are always interested in having to optimize both computation time and sample complexity, this is simply a trade-off that you might be accounting for and that you need to trade off in practice. So that's it for uncertainty propagation in model-based RL. And let's see you in the next summary video.